In this video, I'll show you how to solve the ALEKS problem called Predicting the Relative Ionic Character of Chemical Bonds. To help you solve this problem, you are going to want to have access to a periodic table, and you might also need to have access to a table of electronegativities. I just did a Google search and pulled up the first thing that popped up. This looks like a periodic table, but it's got electronegativity values listed on it. So what we do know, just for starters, is that ionic character is dictated on the difference in electronegativity of the elements that are in the bond, and in a short, kind of like a shortcut, the further apart the elements are in terms of their location on the periodic table, the further they are apart from each other, the more ionic the bond will be. And the closer they are to each other, the closer together they are, again, this is referencing their location on the periodic table, the less ionic the bond will be. So for a lot of these problems that I looked at, I was able to solve the problem just by looking at the elements' relative locations on the periodic table. Didn't need to consult a table of electronegativities. So that should be the first thing that you try. And when you look at the four compounds that you're comparing, you're going to notice that all four of those compounds have one element in common. So for me, all four of my compounds have the chlorine element in common, and I am just going to kind of highlight that chlorine element on the periodic table is located right here. And then I'm going to find the other elements in all four of these compounds. So I have potassium, Si, Al, and Sr. The potassium is right here. And these elements are pretty far apart on the periodic table. That means that it's going to be a pretty ionic compound. I have Si, which is located right here. They're pretty close together, not very ionic. I have aluminum, which is right next to Si, also pretty close together, not very ionic. And then I have strontium right here, pretty far apart from chlorine. That's also going to be pretty ionic. So what I can say for sure is that the silicon and the chlorine are closest together compared to Al, Sr, or K. So these two are the closest together, and that means that that bond, the closest together, that bond is going to be the least ionic of all four of these. ALEKS is ranking that with a 4, and it says that it is the least ionic. The next closest together is the aluminum and the chlorine. So those are pretty close together as well. Not as close as SiCl, but they're still pretty close together. So that is going to be my number 3. The aluminum is my number 3. And then I have strontium and potassium. And those distances are kind of difficult for me to eyeball on the periodic table just because of sort of the diagonal between K and Sr. Makes it a little bit trickier. If I had like this guy down here, that would be easier for me. I would be able to say that this distance is greater than this distance, and therefore this was more ionic because they're further apart. But it's kind of hard to tell with potassium and strontium, and that's when the table of electronegativities is going to come in handy. So I've got my table of electronegativities over here, and I am going to just kind of write down my electronegativity value for potassium is 0.82, for strontium it is 0.95, and we'll also write down the value for chlorine as well. It is 3.16. If we have to actually calculate the differences in electronegativity to use that to help us come up with a ranking of ionic character, we're literally just looking at the difference between the electronegativity of the two elements in the bond. So the difference in electronegativity between 3.16 and 0.82, that's for my potassium. And I'm comparing that to the difference in electronegativity between chlorine, 3.16, and strontium, 0.95. And without even busting a calculator out, this is going to be a bigger number. We could pull a calculator out and do the math, but this is going to give us a larger number when I do the subtraction, which means, and in fact, like we could actually, if we wanted to, we could actually do it. Let's actually do it. 3.16 minus 0.82 is 2.34, and 3.16 minus 0.95 is 2. See, they're very, very similar, which is why it's really hard to just kind of gauge by their positions. The larger the difference in electronegativity, the more ionic the substance is. So that means that Potassium is my most ionic, and then the strontium is my next most. So hopefully for the problems that you get, most of them you're not going to need to use a table of electronegativities. You'll be able to calculate it just based on the relative distances between the elements, but just in case you do, this is how you would go about doing it.